Hey everybody, welcome to video 7-1, and we are going to be talking about some theorems with the interior and exterior angles of a triangle. Still talking about triangles like we were in the last two modules, but just wanted to kind of walk you through this very important theorem, which is the triangle sum theorem, and that is simply that the sum of the angle measures of a triangle will always add up to 180 degrees. Instead of just knowing this, I wanted to show you one proof to kind of tell you how we come up with that. So if we're looking at page 313 here, part D, we are going to do the rest of the page, but we're going to do it in class, so don't worry about the explore for now. Part D, if you take a look at it, we have a proof with a triangle ABC, and we have a new line that's drawn through point B across the top. They call that an auxiliary line. It's basically an extra line that you add to a proof in order to help you do the proof. So we're going to fill in the rest of this. It says first draw a line through point B parallel to AC. That's the parallel postulate. That means that you can draw a line through any point parallel to another one. Statement 2 simply says measure of angle 1 equals something and the measure of angle 3 equals something. Well, if we take a look at the diagram, measure of angle 1 would be the same as the measure of angle 4, and measure of angle 3 would be the same as the measure of angle 5. So we're looking at, I think you can see, alternate interior angle theorem. Both of those are alternate interior angles. Then the next statement says that the measure of angle 4 plus 2 plus 5, and those are the three angles that are across the top on our auxiliary line here at point B. We just simply say that that's the angle addition postulate. They add up to 180 because this is a straight angle here. So then notice what I can do is, since measure of angle 1 is equal to measure of angle 4, then in place of measure of angle 4, I can put the measure of angle 1. And then if the measure of angle 3 we had stated equal to the measure of angle 5, then in for measure of angle 5, I can put the measure of angle 3. And you guys, that's just a straight up substitution. And so what I've proven is that all three angles in the triangle add up to 180 degrees. Now on the next page, page 314, we're going to extend that idea that all the angles in a triangle add up to 180 degrees into exploring the angles in other size polygons. So polygons is just another name for shape, you guys, many-sided figure. And in a polygon, it has always straight sides. And we are talking about how to break up each individual polygon into a certain number of triangles. And this table at the bottom of the page keeps track of that information. So let's just see what we can do here. If we're looking at part A, it says draw the diagonals from any one vertex for each polygon. So we're going to pick a vertex and see if we can draw a diagonal. Now remember what a diagonal does. It connects any two non-consecutive vertices in a polygon. In other words, it connects 2 points, 2 corners of a polygon that are not directly next to each other, because connecting them next to each other would simply be redrawing a side, okay? So for the triangle, for the triangle to begin with here, we can't draw any diagonals that aren't drawing to other corners and redrawing a side. So that doesn't work. So there's no other triangles that we can split that triangle into. However, in the quadrilateral, let's say we pick this vertices right here, vertex right there in the corner. What we can do is draw across the figure, and we can split that quadrilateral into 2 triangles. If we look at the next figure, which is a pentagon, we can take this vertex at the top here, and we can draw not to this side and this side, but we can go across and we can split this pentagon into 3 triangles. The hexagon underneath the triangle here, again, pick any vertex you want, doesn't have to be the one I'm choosing, and then connect across to as many places as you can from that one location though. So there's 3 diagonals I can add to that picture, and then look, we have 1, 2, 3, 4 triangles. So we'll write that down. Keep going through that process. Pick any corner you want. Draw as many diagonals as you can. Count them up. 1, 2, 3, 4, 5 for our, looks like a 7-sided figure. And for our octagon, our nice little stop sign here, we'll pick a corner. I'm going to pick one down at the bottom this time. And we'll go across. I can't go to the one next to it, but we can go to this one, this one, this one, this one, and this one. And that makes, count them up, 1, 2, 3, 4, 5, 6 triangles. Okay, so if what I know is true about a triangle, that is that all the angles have to add up to 180, then depending on the number of triangles I can split the polygon into, that's going to give me the total number of angles in the polygon. So if we go down the page here to the table and we fill in some information that we just drew, starting with our pentagon, which has 5 sides, and it was split into 3 triangles, then instead of 1 triangle times 180 or 2 triangles times 180 like it was for the quadrilateral, this is going to be 3 triangles times 180 or 540 degrees, you guys. A hexagon has 6 sides. We determined that it could be split into 4 triangles, and therefore that's 4 times 180 or 720 degrees. And then finally a decagon, you guys, that has 10 sides. I hope that you're starting to see a pattern here. 3 down to 1, 4 down to 2, 5 down to 3, 6 down to 4. There's a difference, a common difference each time between these columns, and that difference is 2. So there would be 8 triangles if I were to sketch a decagon, and that would be 8 times 180 or 1,440 degrees. Let's go to the next page. Part C says, do you notice a pattern, we've already started to, between the number of sides and the number of triangles? And yes, definitely, it's 2 less. So if n represents the number of sides, how can you represent the number of triangles? Well, that would be, you guys, n minus 2. So make a conjecture for a rule that would give the sum of all the inside angles of any n-gon or polygon. The sum of those interior angle measures is simply going to be the number of triangles we could form, or n minus 2 times 180 degrees. Let's reflect a little bit. In a regular hexagon, how we could use the sum of the interior angles to determine the measures of each interior angle. Focus there on the word regular. If it's a regular hexagon, remember, that means all of the angles are the same size. And so if I know the sum of my interior angles, all I would have to do is divide it by the number of angles. And if it's a hexagon, we would just simply take the sum of those interior angles and divide it by 6. How might you determine the number of sides for a polygon whose interior angle sum is 3,240? Well, we don't necessarily know the number of sides, but we do know the formula that we've come up with here, which is n minus 2 times 180, and the sum is 3,240. So we just are going to solve this equation. What I would recommend to you guys is that you go through and divide by the 180 because it'll make your equation much more manageable as far as the numbers that you're dealing with. So 3,240 divided by 180 on my calculator gives me a right-hand side of this equation of 18. And then I still have the n minus 2 over here. Simply solving for n by adding 2 to both sides, we get n is 20. Okay, so now what we're going to do on page 315 here, we've already talked about how to come up with this polygon angle sum theorem, super important, make sure you highlight it. But what we're going to do is we're going to start using it and finding missing angles in some figures, okay? So in part A, it says for the nonagon shown, now first off you should know that a nonagon is a word that means 9 sides. Find the unknown angle measure x. So first we're going to use the polygon angle sum theorem to find the sum of the interior angles when n equals 9. That's 9 minus 2 times 180 right here. And that's 7 times 180, or 1,260 is my total of all those 9 angles. So if I look at my diagram, I've got x plus 125 plus 130 plus 172 plus 200 plus 140 plus 102 plus 98 and plus 135 that all have to equal up to 1260. And then I'm just going to use my calculator, you guys, and subtract all these 8 known angles, and we're going to get that the unknown angle measure is 158. Hopefully pretty straightforward. Let's go to the next example. So I'm at the top of page 316 here, you guys, and we're going to determine the unknown interior angle measure of a convex octagon, highlight that word, in which the measures of the 7 other angles have a sum of 940 degrees. Now we don't have a diagram to go on, but we do have some good given information. First off, we know that the octagon means that we have 8 sides. And so if we want to find a value for the sum of all 8 of those angles using our polygon angle sum theorem, it's going to be 8 minus 2 times 180, or 6 times 180, or 1,080 degrees. So what I'm going to do is I'm going to set up an equation with the 940 that I know that the 7 other angles add up to, plus my unknown 8th angle, and I'm going to set that equal to the sum that I just found of 1,080 degrees. Do a quick subtraction here, and you should get that the unknown angle is 140 degrees. Actually, you should probably wait to put your degree symbol in until after you solve for x, but it's 140 degrees. All right? So number 5 says, how might you use the polygon angle sum theorem to write a rule for determining the measure of each interior angle of any regular convex polygon with n sides? Okay, think back to what we did on the previous page. We talked about a regular hexagon. What if we don't know how many sides it has? Well, you guys, our formula is very simple. We're going to still take our n minus 2 times 180 polygon angle sum theorem there, and that formula gives us the total number of degrees of all of the angles put together. And then remember, we are going to divide because it is a regular polygon, so we can divide and say that each angle is going to be the same amount, but we may not know how many sides. We're saying that the number of sides is n, so we're simply going to divide that by n. Alright, you guys, I would like for you to do, if you would please, the your turns at the bottom of this page before you move on to video 7.1b. So you do 6, 7, and 8 and see what you can do with those polygon angle sum theorem problems. Number 6, 7, and 8. And we'll see you in the next video.